Welcome to Basic Electrical Engineering lecture series. This is a series of lecture videos for the first year engineering and electrical diploma students. In these videos, fundamentals of DC and AC circuits, network theorems, fundamentals of transformers, DC and AC machines, and renewable energy sources are the topics covered. Sufficient number of numericals are worked out in each session to make the concepts clear to the viewers. For a basic idea about the topics mentioned, please watch these videos from the very beginning itself. If you find the videos useful, please subscribe for the channel, like the video and press the bell icon for notification. Please try to wear a headphone and watch the video for better sound clarity. Thank you all. And now let's start with today's session. This is the first session of the electrical engineering lecture series. In this session, Ohm's law, power and energy, these are the topics covered. So most of you are familiar with the very fundamentals. So I'll give a brief introduction about the theory part and then we'll start working out few examples. So Ohm's law, as you know, it states that the ratio of potential difference between any 2 points on a conductor to the current flowing between them is a constant provided the temperature of the conductor does not change. Or equation wise, if we put it, it is V by I is equal to R. That is, in a conductor between any 2 points, the ratio of potential difference and the current flowing between them is a constant. So, provided the temperature of the conductor does not change. Say in a conductor a current I is passing and between 2 points A and B the potential difference produced is V volts, then V by I is the resistance of the conductor between the points A and B. That is the statement of Ohm's law. So the ratio of potential difference to current between any 2 points in a conductor is a constant provided the temperature of the conductor does not change. So this is one equation for R. The resistance of a conductor we can find out by measuring the voltage across it and dividing it with the current flowing through the conductor. Also there is another equation, R is equal to rho L by A. So resistance is directly proportional to the length of the conductor. So here if we take this case also, the resistance of this conductor between points A and B, take, it is proportional to the length of the conductor. Here the length of the conductor is the length of the portion between A and B. Cross-sectional area of the conductor, the resistance is directly proportional to the length of the conductor and inversely proportional to the cross-sectional area of the conductor. And so also it depends on the nature of the material with which the conductor is made. So conductors are normally of copper or aluminum. These are the commonly used. Silver is also a good conductor of electricity. So silver, copper, aluminum, like that, different materials are there. So the resistance of a conductor is directly proportional to its length, inversely proportional to the cross-section area of the conductor, and also it depends on the nature of the material. So silver, comparing these three conductor materials, that is silver, copper and aluminum, silver is having the least resistance, copper resistance is more and aluminum resistance is more for still more for a particular resistor of the same dimension, same length and same cross-sectional area. So if you assume three conductors having the same length and same cross-sectional area, its resistance, the resistance will be least for silver conductor, little more for copper conductor, and still more for aluminum conductor. So R is equal to rho L by A. Rho is a quantity which is called the specific resistance of the material. Specific resistance, by definition, it is the resistance across the opposite sides of a cube of that material. Say if we take a copper, you assume a cube of copper, 1 meter length, 1 meter breadth, and 1 meter height. Measure the resistance of the cube across the opposite faces. Whatever resistance you are getting, it is numerically equal to the specific resistance of that material. So specific resistance, by definition, it is the resistance across the opposite faces of a cube of that material. Take a cube of that material of 1 meter length, 1 meter breadth, and 1 meter height. Then measure the resistance of this cube across the opposite faces. That is numerically equal to the specific resistance of that material. So R is equal to rho L by A, or rho is equal to R into A by L. R is in ohm, area meter square, length in meter. So solving, its unit is equal to ohm meter. So in SI units, the unit of specific resistance is ohm meter. R in ohms, A in meter square, L in meter. So simplifying, you will get it as ohm meter. Now the major relationships, you must be knowing this. Resistors are connected in series. The equivalent resistance is the sum of the resistances. Say if n number of resistors are connected in series, R1, R2, R3, Rn, the equivalent resistance is equal to R1 plus R2 plus etc. to Rn. So when resistors are connected in series, the equivalent resistance is the sum of the individual resistances. So when they are connected in parallel, R1, R2, like the 10 number of resistors are there, the equivalent resistance between points A and B, here also between points A and B. So here in this case, R equivalent, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by Rn. That is the equation for finding out the equivalent resistance when they are connected in parallel. So one point to remember, which is very useful, is if there are only two resistors, R1, R2. So 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So R2 plus R1 divided by R1, R2. Therefore, R equivalent is equal to R1, R2 divided by R1 plus R2. So when there are only two resistors, like take product divided by sum, that is the equivalent when they are connected in parallel. Say if 5 ohm and 10 ohm resistors are connected in parallel, so the equivalent will be 5 into 10 divided by 5 plus 10. 5 into 10, 50, 5 plus 5 plus 10, 50. So 50 divided by 15, that is the equivalent resistance. So remember this relation, because in most of the numericals, you will come across the occasion where there are two resistors connected in parallel, especially when you are simplifying networks. So if two resistors are connected in parallel, the equivalent is the product divided by sum. So R1, R2 divided by R1 plus R2 is the equivalent of two resistors when they are connected in parallel. Then current division. This is another important relationships should to be remembered. Now there are two resistors connected in parallel. A current of I ampere is coming to, say, the common points are A and B. There are two resistors connected in parallel. How the current will divide between the two resistors R1 and R2. Now you can find out the currents flowing through R1 and R2 by this relationship. Say, for example, assume a voltage V is applied across the parallel combination. So the total current I is equal to total current passing through the circuit is equal to V divided by R equivalent. The total current taken by the parallel circuit is V divided by equivalent of R1 and R2 in parallel. So this is equal to V divided by R1 and R2 in parallel. The equivalent is R1 R2 divided by R1 plus R2. Now in this relation, so I is equal to V divided by R1 R2 divided by R1 plus R2. In this relation, take V divided by R1 separately. So V divided by R1 is equal to I into R2 divided by R1 plus R2. But V divided by R1, V is the voltage across this parallel combination, and I is the total, V is the voltage across the parallel combination. That means the V is the voltage across R1 as well as R2. So the current through R1 is equal to V divided by R1. So the voltage across points A and B is V. That means the voltage across R1 is V. Voltage across R2 is also V. The current through R1 is equal to V divided by R1. So V divided by R1 is nothing but I1. So I1 is equal to I into R2 divided by R1 plus R2. That means the current through any branch is equal to the incoming current. So current coming to the node A into resistance on the opposite side. That is, we want to find the current through R1. Resistance on the opposite side is R2. So I into R2 divided by sum of the resistances. R2 divided by R1 plus R2. So likewise, if we take V divided by R2 from this equation, you can prove that I2 is equal to I into R1 divided by R1 plus R2. So I2 is the current flowing through R2 is equal to total current coming to the node into opposite side resistance. We want to find the current through R2. So opposite side resistance is R1. R1 divided by R1 plus R2. So this is a very useful relationship which we can use while simplifying networks. So likewise, voltage division in series circuits. So there are three resistors R1, R2, R3. A voltage V is applied across it. So there will be a current through the circuit I. I is equal to V divided by R1 plus R2 plus R3. So the voltage across R1, that is V1, is equal to I into R1. Likewise, V2 is equal to I into R2, and V3 is equal to I into R3. So total voltage V is equal to V1 plus V2 plus V3, or I into R1 plus R2 plus R3. So this is how the voltage divides in a series resistive network where there are resistances. Now in this case there are three resistors R1, R2, R3. To find the voltage across the individual resistors, you have to find the total current, that is V divided by R equivalent. V divided by R equivalent is R1 plus R2 plus R. So V divided by R equivalent will give you the total current. The current into individual resistance. That is I into R1 will give V1, I into R2 will give V2, I into R3 will give V3. Then power. So in DC networks, power is the product of voltage and current. The unit is watt. Also, it is equal to joules per second. So power you can, the equation for power is either VI, but V is equal to I into R. So you can write it as I square R. V is equal to I into R. Substitute I into R into I square R. Or I is equal to V by R. So it's also is equal to V square by R. So you can use any one of these equations. It's either VI or I square R or V square by R. So using any one of these relationships, you can find out the power in a DC circuit. So power is equal to I square R or V square by R or VI watts in DC circuits. So energy is nothing but power into time. So it is VI into T or I square R into T or V square by R into T. That is the equation for energy. Energy is measured in joules in SI units. So, but the practical unit of energy is kilowatt hour. So, kilowatt hour is also commercially known as unit. Commercial unit of electricity is, or commercially, this is 1 kilowatt hour is known as 1 unit. So, for our domestic power energy meter, say the power consumption in a particular month is 100 units or 200 units. What's meant by unit? Unit is kilowatt hour. 1 unit is 1 kilowatt hour or 1000 watt hour. So 1000 watt into 3000 seconds. So 1 kilowatt hour is known as 1 unit. So but in also instead of kilowatt hour, certain cases megawatt hour is also used. Megawatt hour or even terawatt hour is also used. Now let's start with a few examples. Find the resistance of the aluminum conductor having a uniform cross-sectional area of 20 centimeter square, length 20 meter and resistivity 2.8 into 10 to the power of minus 8 ohm meter. Find the resistance of the aluminum conductor having, this is the cross-sectional area. So this is the length of the conductor. So length is 20 meter. Cross-sectional area is 20 centimeter square. So centimeter square is to be converted to meter square. For that, you have to multiply with 10 to the power of minus 4. 100 centimeter is equal to 1 meter. So centimeter square to meter square multiply with 10 to the power of minus 4. So cross-sectional area in meter square is 20 into 10 to the power of minus 4 meter square. So length and cross-sectional area both are in standard units. So before working out the problem, check whether all the specifications are in standard unit. Then otherwise you have to convert wherever necessary. So here length of the conductor is 20 meter. Cross-sectional area length of the conductor is 20 meter. That's in correct unit. Then cross-sectional area 20 centimeter square. It's to be converted to meter square. Resistivity is in ohm meter only. The specification is correct in standard unit only. So we can substitute and find the resistance of the conductor. Rho 2.8 into 10 to the power of minus 8 into L 20 meter divided by cross-sectional area 20 into 10 to the power of minus 4 meter square. So this is the resistance of the conductor. 2.8 into 10 to the power of minus 4 ohm. Now next we have to find the current supplied by the source in the given circuit and also find the current through R5. R5 is this resistor. Find the current supplied by the source. So for that we have to simplify the network. So what is the total resistance connected across the 20-volt battery we have to find. Then 20 volt divided by the equivalent resistance connected across the battery. That will give the total current. Then total current we have to divide among different resistors in the network. So for that, to find out the equivalent resistance, we have to start from the far end. R4 and R5 both are connected across. I'll mark the terminals as A, B, C, D. So R4 and R5 both are connected across C and D, the same terminals. So R4 is connected between C and D. R5 is also connected between C and D. So these R4 and R5, these resistors R4 and R5 both are in parallel. So the equivalent is when two resistors are connected in parallel, the equivalent is product divided by sum. So the equivalent is R4 R5 divided by R4 plus R5. 20 into 20 divided by 20 plus 20. 20 into 20 divided by 40. That is 10 ohm. 10 ohm is the equivalent resistance of R4 and R5. Now I'll redraw the circuit. 20 volt. R1 is equal to 10 ohm. This is terminal A. Between A and B, there is a resistor R3 which is 20 ohm. Between A and C, resistor R2 10 ohm. Then between C and D, we simplified it to this 20, we simplified it to 10. Now you can check. This is a series circuit. A, C, D. A, C, D. It is a series circuit. That means these two resistors are connected in series now. So we can simplify it to a single resistance. 10 and 10 are connected in series means equivalent is 20. So I'll replace it with a 20 ohm resistor. Now you check. These two 20 ohm resistors are connected in parallel. B and D are the same points now because it is a short. So 20 and 20 are connected in parallel. Again 20 into 20 divided by 40. That is 10 ohm equivalent. So when two equal resistors are connected in parallel, equivalent is the half of that. So the equivalent is 10 ohm now. Two 20s in parallel, 10. Now check. These 10 and 10 are connected in series. So the equivalent is 10 plus 10. So these two we can add, make it a single resistor of value 20 ohms. So the total resistance connected across the battery is now 20 ohms. So therefore the current is 20 divided by 20. So I is equal to 20 volts divided by 20 ohm, that is equal to 1 ampere. So the total current supplied by the network is 1 ampere. So what we did now, we reduced the network to a single resistance. So there are two R4 and R5 are in parallel because both are connected across the same terminal C and D. So 20 into 20 divided by 40 equivalent is 10 ohms. So both the R4 and R5 both are 20 ohms. So when they are connected in parallel, equivalent is half of that because R4 is equal to R5. So that is 10 ohm. So that 10 is connected coming in series with R2. So 10 plus the equivalent of these two, that is 10. 10 plus 10, 20. That means till here we simplified the network. So we got R4, R5 in parallel, that is 10 added to R2, 10 plus 10, 20. Now two 20s are coming in parallel. Ignore the circuit towards the right. So these two 20 in parallel, again it will become 10. So I'll draw one more line. So these two 20s in parallel, we can replace with a 10 ohm resistor. So 10 plus 10, 20. That is the total resistance coming across the circuit. So 20 by 20 is 1 ampere. 1 ampere is the total current supplied by the battery. Now the next part of the question is we have to find the current through R5. That is this resistor. So let's see how it will divide. So this is junction A, this is B, node A, node B, this is node C, node D. See, B and D are the same. Okay, now these two 20s are connected in parallel, equivalent is 10. So 10 added to this 10 is 20. So towards the right of the circuit, you ignore it, take this as 20. Because we simplified. So 20 is the equivalent of R2, R4 and R5. 10 plus equivalent of R4 and R5, another 10, that is 20. Now 1 ampere is the current coming to junction A. It will divide between R3 and this 20 ohm resistor. R3 is 20, this is also 20. So use the current division formula. So incoming current 1 ampere into, we have to find out the current through this resistor because we have to pass it on to the right. Ultimately, you have to find the current through R5. So we have to find the current through this 20 ohm resistor. That is 1 ampere into opposite side resistance R3, that is 20, divided by sum R3 plus this 20, 20 plus 20, 40. That's equal to 0.5 ampere. So this in current coming 1 ampere current coming to node A will equally divide because these resistors are equal. Current will equally divide between them. 1 ampere will divide into 0.5 and 0.5. So current through this branch is 0.5 and this is 0.5. Now current coming to node C is 0.5 ampere. It will divide between R4 and R5 again equally. We don't have to use current division formula because the resistors are equal. So when they are equal, it will divide equally. That is 0.5. This current will be 0.25. This also will be 0.25. If you want to check it using the current division formula, you can check. Current through R5 is equal to IR5 is equal to incoming current 0.5 ampere into opposite side resistance, that is 20 ohm. Opposite side resistor is R4 into 20 divided by 20 plus 20, that is 40. That is 0.25 ampere. So 0.25 ampere is the current through resistor R5. So the next problem is, if the power dissipated in R4 is 1.25 watt, find the battery voltage. Power dissipated in R4 is 1.25 watts. Find the battery voltage. Battery voltage V1 is not given. We have to find it out. The given information is that the power dissipated in resistor R4 is 1.25 watts. I'll mark the terminals A, B, C, D. Now resistor R4 is connected between terminal C and D. Likewise, one more resistor is there. R5 is also connected between terminal C and D. So I'll assume a voltage across it. Now, from the given information, that is power dissipated in R4 is 1.25 watts. So the voltage across R4 is V. V is the voltage across terminal C and D, and R4 is connected between terminal C and D. So voltage across R4 is V. So V square divided by R4 is equal to 1.25. So power is equal to V square by R. So R4 value we know, that is 20 ohm, that is V square divided by 20 is 1.25, or V square is equal to 20 into 1.25, that is 25, therefore V is equal to 5. So V is equal to 5 volts. So from the given information, it's given that the power dissipated in resistor R4 is 1.25 watts, and voltage across, let's assume a voltage of V across terminal C and D. So V square divided by R4 is 1.25 watts, because R4 is connected between C and D. We are assuming a voltage V across C and D. So V square divided by R4 is 1.25. So R4 is 20 ohms. So V square divided by 20 is 1.25. So V square is 20 into 1.25, 25. So V is equal to 5 volts. So if V is equal to 5 volts, then we can find the current through R4 as well as R5. V is the common voltage across points C and D. So current is equal to V by, current through R4 is V by R4. Current through R5 is V by R5, because V is the common voltage. So V is 5 volt, R4 is 20, so current is 5 by 20, 5 by 20 is 1 by 4, or 0.25 ampere. R5 is also 20, so V is 5 volt, R5 is 20 ohm, so current through R5 is 5 by 20, that is 0.25. So the total current must be 0.25 plus 0.25, that is 0.5 ampere. So we can find the current through R2 by adding these two. That is, from C to D, the current is 0.25 ampere. From C to D through R4, the current is 0.25 ampere. Add these two, you will get the total current. So current, since the battery polarity is here, the current must be flowing in this direction only. So V, this is the positive. So at point C is positive with respect to D. The potential difference is 5 volts. Now current through R2 is 0.5 ampere. Value of R2 is 10 ohms. Therefore the voltage across A and C is equal to 0.5 into 10, that is 5 volts. 0.5 ampere, R2 is 10 ohm. So voltage potential difference across points A and C, or potential difference across R2, is equal to 0.5 into 10, 5 volts. So current is flowing like this. So this should be the positive of the, so this 5 volt should be positive with respect to, or positive at point A. So this is the polarity. A is positive with respect to C. So from this is the negative of the battery, B or D. So from D to C, the potential difference is 5 volts. C to A, the potential difference is 5 volts. So 5 plus 5, 10. 10 volt is the potential difference between A and B, because B or D both are same. Ground potential 0 volts, let's assume. B and C, the potential difference is 5 volt. C and A, the potential difference is 5 volts. So adding in this polarity, this is positive here, this is positive here. So this 5 and 5 can be added. So the total is 10, 10 volt. So the voltage across R3 is 10 volt, value of R3 is 20. So current through R3 is 10 divided by 20, that is 0.5 ampere. So with this information, we got the voltage between A and potential difference between A and B. So that divided by R3 is the current through R3. So 10 divided by 20, 0.5 ampere. 0.5 ampere is the current through R3. It is flowing from A to B because A is positive with respect to B. Now we got this current. Current from A to B is 0.5 ampere. From A to C is 0.5 ampere. Therefore, the total current is 1 ampere. So the voltage across resistor R1 is equal to 1 ampere into 10 ohm. That is 10 volts. So the voltage between these 2 points across the battery terminals is 10 plus 10, that is 20 volts. So the battery voltage is 20 volts. So once more I'll tell you. So it is given that power dissipated on resistor R4 is 1.25. Let's assume a voltage between these 2 points, V volts. So this is C, D, this is A, B. So let's use the equation for power. Power is V square divided by R. So R4 is connected between C and D. R5 is also connected between C and D. It's a parallel combination. So V square divided by R4 is power dissipated in R4, which is 1.25. So V square by 20 is 1.25. Solving, we will get V as 5 volts. This should be the polarity because battery positive is here. Current can flow only in this direction. So V is equal to 5 volt. Once we get V, we can find out the current through resistors R4 and R5. 5 divided by R4, that is R4 is 20. So 5 by 20, 0.25 ampere is the current through R4. Likewise, current through R5 is 5 divided by R5. So 5 divided by 20. So that is also 0.25. So this current is 0.5 ampere. 0.25 plus 0.25, it is 0.5 ampere. So we can find the voltage across R2 because value of R2 is 10 ohm. Current is 0.5 ampere. 0.5 into 10 is 5 volts. So now find the voltage between A and B. That is, B is same as D, or from B to C. B, D, both are the same points only. From B to C, the voltage is 5 volts. C to A, it is 5 volts. Therefore, the total is 10 volts. This is 10 volts. Now we know the voltage across R3, that is 10 volts. R3 value is 20 ohms. So current through R3 is 10 by 20, that is 0.5. So the total current is 0.5 plus 4. From A to B, 0.5, A to C also 0.5, adding it is 1 ampere. So 1 ampere is the total current supplied by the battery or the current passing through R1. So we can now find out the voltage across R1, which is equal to 1 ampere into 10 ohm, that is 10 volts. So we know that the potential difference between B and A is 10 volt. A and battery positive another 10 volt. Adding 10 plus 10, 20. 20 volt is the voltage across the battery, or battery potential is 20 volts. Now next, a current of 20 ampere is flowing through two ammeters A and B connected in series. The potential difference across A is 0.2 volts and across B is 0.3 volts. Find how the same current will divide when they are connected in parallel. A total current of 20 ampere, or a current of 20 ampere is flowing through two resistors, two ammeters A and B. Here we have to consider only the ammeter resistance. Resistance of first ammeter is R1. Resistance of the second ammeter is R2. So the voltage across R1 or across ammeter 1 is 0.2 volts. Voltage across ammeter 2 is 0.3 volts, or voltage across R1 is 0.2 volts, voltage across R2 is 0.3 volts. We have to find out how the same current will divide when they are connected in parallel. So the current is 20 ampere. Resistance value we have to find out. We know the voltage across the resistor R1 is 0.2 volts. Current is 20 ampere. Voltage is 0.2 volts. Therefore, R1 is equal to 0.2 divided by 20. That is 0.01 ohm. So current is 20 ampere. A current of 20 ampere is flowing through a resistor R1. And the potential difference produced is 0.2 volts. So the value of the resistance is V by I, 0.2 divided by 20, 0.01. Now the same current is passing through the next ammeter also, that's 20 ampere. So the potential difference produced is 0.3 volt. So value of the resistance is V by I, 0.3 divided by 20, or 0.015. So from the given data, we can find out the resistance of first ammeter and second ammeter. Ammeter 1 has a resistance of 0.01 ohm, ammeter 2 0.015 ohm. So here R1 is equal to 0.01, R2 is equal to 0.015. Now we have to find out how this current of 20 ampere will divide between these two resistors R1 and R2, or between these two ammeters A and B. This is ammeter A, ammeter B, this is ammeter A, ammeter B. Now let us take the current through ammeter A as IA. So this current as IA. IA is equal to, let's use a current division formula. 20 ampere into resistance on the opposite side. that is R2 divided by R1 plus R2. That is 20 ampere into R2 is 0.015 divided by 0.01 plus 0.015. That is 20 into 0.015 divided by 0.025. That is 12 ampere. Simplifying this, we can get 12 ampere. So IB is naturally 20 minus 12 is 8 ampere, or use the equation and find out. 20 into 0.01 divided by, this is 0.01 plus 0.015, that is 0.025 is equal to 8 ampere. So from the given information, we found out the values of the ammeter resistances. First ammeter A has a resistance of R1. We can find it out by dividing the voltage across R1 with current through R1. Voltage across R1 is 0.2. Current through R1 is 20 ampere. 0.2 by 20 is the value of resistance of first ammeter. Second ammeter likewise V divided by I, that is 0.3 by 20, 0.015. Now a current, when the ammeters are connected in parallel, like a total current of 20 ampere is coming to the common point. We can find out the current through the ammeters by using the current division formula. IA is incoming current into opposite side resistance by sum of the resistances. IA is 20 into opposite side resistance is 0.015 divided by sum is 0.01 plus 0.015. We'll get it as 12 ampere. Current through the other branch is total current minus current through the first branch. 20 minus 12, that is 8 ampere. Now the next one, a circuit consists of two parallel resistors having 20 and 30 ohms, 20 ohm and 30 ohm connected in series with 15 ohm. 15 ohm resistor. So parallel resistors having resistances 20 ohm and 30 ohm connected in series with 15 ohm. If the current through the 15 ohm resistor is 3 ampere, find the current in 20 ohm and 30 ohm resistors. Also the voltage across the whole circuit, power consumed by each resistance and total power. Okay. First, let's find the current in 20 ohm and 30 ohm resistors. You can see easily find it out because this current is 3 ampere. Current through R3 is 3 ampere. That means the incoming current is also 3 ampere. Now, how 3 ampere will divide between 20 ohm and 30 ohm? So, let's take this I1 and take this current as I2. So, I1 is equal to current coming to the junction into opposite side of the resistance, that is 30 divided by sum of the resistances, 30 plus 20, 50. So 3 into 30 by 50, that is 1.8 ampere is the current I1. I2 is 3 minus 1.8, you can take over. 3 minus 1.8 is 1.2, or 3 ampere into opposite side resistance is 20 divided by sum of the resistance 20 plus 30, 50 is equal to 1.2 ampere. So I1 is 1.8 ampere, I2 is 1.2 ampere. Now the voltage across the whole circuit. So for that, the 3 ampere into R equivalent is the voltage across the whole circuit. 3 ampere into the equivalent of, this is R equivalent. This is 3 ampere. So 3 square into R equivalent is voltage. 3 into R equivalent is the voltage across the whole circuit. Say I'll mark it as points A and B. We have to find the potential difference between points A and B. That's equal to 3 ampere into equivalent resistance connected between A and B. So R equivalent is equal to, this is a parallel combination of 20 and 30. 20 into 30 divided by 20 plus 30, 50 plus another 15 ohm. That is this one. So equivalent of the parallel combination 20 into 30 divided by 20 plus 30, that is 50, plus this R3, that is 15 ohm. So 20 into 30 divided by 20 plus 30 plus 15, you will get it as 27 ohms. So the voltage across the whole circuit is VAB is equal to 3 into 27. 7 to 3, 21, 81 volts. 81 volts is the voltage across the whole circuit. Then power consumed by each resistor and total power. So power consumed by R1 is 1.8 square into 20. So P1 is equal to 1.8 square into 20. So here P2 is equal to 1.2 square into 30. Power dissipated in R3 is, so P3, 3 square into 50. 1.8 square into 20, this is equal to 64.8 watts. 1.2 square into 30 is 43.2 watts. Here 3 square into 15 is 135 watts. Add all this, you will get the total power. So power consumed by each resistor and total power. Power consumed by R1, R2, R3. So add all that, you will get a total power. Or you can also find it out. So 27 I square R, 9 into 27. 27 is the equivalent resistance of the whole circuit into 9. 243 watts you will get. So the voltage across the whole circuit is 81 volts. And power consumed by each resistance we found out total power. Adding all that, or from this circuit also you can find out the total power. Now this question, find EA. What is the potential difference between terminals E and A? So for that we have to straighten the circuit. This is point E. So battery negative is connected. We have to find the potential difference between E and A. So like this, tracing is difficult. If we straighten it, then easily we can make out which terminal is positive with respect to each node. This is negative, this is positive. Positive is connected to D, B and C. Positive is connected to next battery 15 volt, positive is connected to D, negative is connected to C. Then third battery, negative is connected to C, positive is connected to B. Then positive is connected to B, negative is connected to A. Check. So between A and B, 20 volt, its positive is connected to B. Then between B and C, this is 10 volt. Positive is connected to B, negative is connected to C. Between C and D, 15 volt, positive is connected to D, negative is connected to C. Between B and D, Positive is connected to D, negative to E. So this is 20 volt. So between C and D is 15 volt. Between D and E is 5 volt. So this is positive, this is positive, this is in the opposite directions. So 20 plus 15, upward direction, downward, 5 plus 10, 35, 20 plus 15 minus 15 is 20 volts. So total is 20 volt. So the potential difference between point C and A is 20 volts with E positive. The net voltage is 20 volt with the terminal E positive. So the next is find the value of R in this circuit. So I'll mark the terminals as A and B. So the equivalent resistance of this parallel combination between A and B is, so it can be found out by the applied voltage is 10 volts, the total current taken is 2.25 ampere, therefore R equivalent is equal to V by I, 10 divided by 2.25 is equal to 4.44. Also R equivalent is equal to, it's a parallel branch, so product divided by sum. So this is 8 plus 2, 10 ohm. The lower branch 5 plus R between terminals A and B. So R equivalent is equal to 10 into 5 plus R divided by 10 plus 5 plus R. So we can equate these two. R equivalent is 4.44 ohm. Here R equivalent is, we have got this equation. We equate these two, that is 50 plus 10R divided by 15 plus R is equal to 4.44. So solving R is equal to 3. Now next, find R1 and R2 if power dissipated in one of the resistors is 33.33 watts. So let's take power dissipated in R1 is 33.33 watts. P R1 is 33.33 watts. So it's a parallel combination R1 and R2, and the voltage across the combination is 10 volts. That means across R1 the voltage is 10 volt, across R2 also the voltage is 10 volts. So power dissipated in R1 can also be found by using the equation V square by R. Here V1 square divided by R1 is equal to 33.33. So V1 is 10, that is 10 square divided by R1 is 33.33. So R1 is equal to 100 divided by 33.33, that is 3 ohms. So we can equate now the parallel combination, the equivalent of R equivalent of the parallel combination is, see, the applied voltage is 10 volts, the total current taken is 5 ampere. So R equivalent is 10 volt divided by 5 ampere, it's equal to 2. So R1 we already got it as 3 ohm. So R equivalent is also is equal to 3 into R2 divided by 3 plus R, or 3 into R2 divided by 3 plus R2 is equal to 2. So R2 can be solved as 6 ohms. So what we did is, we assume that power dissipated in resistor R1 is 33.33 watts. The voltage across the parallel combination is 10 volts. So the power dissipated in R1, for that we can use an equation V1 square divided by R1. So V1 is 10 volt. So V1 square by R1, 10 square by R1 is equal to 33.33, from which R1 can be found, which is 3 ohm. Now the equivalent resistance of the circuit can be found by dividing the applied voltage by the total current taken by the circuit. 10 by 5, that is 2 ohm is the equivalent resistance of the parallel combination. Also it's equal to, we found out the value of R1, that is 3. 3 into R2 divided by 3 plus R2 is the equivalent resistance across terminals A and B. Equating these two, 3 into R2 divided by 3 plus R2 is equal to 2. We can solve for R2, which is 6 ohms. So next is find R if total power dissipated in the circuit is 10 watt. So in this case, the total power dissipated is 10 watts. That is in all these three resistors. This is 12 ohm, 8 ohm, and this is unknown. So the R equivalent can be found by, or R equivalent is equal to R plus equivalent of 12 and 8 in parallel. 12 into 8 divided by 12 plus 8. So that is 4.82. That is R equivalent is equal to R plus 4.8. So total power dissipated is given, that is 10 watt. That is in all the three resistors. It's equal to 10 watt. So, or applied voltage divided by, so total power is 10 watt. That is equal to the power dissipated in the combination of the resistance, that is V square by R equivalent. V square by R equivalent. So V is 10. So 10 square divided by R plus 4.8 is equal to 10. Or R plus 4.8 is equal to 100 by 10, 10. So R is equal to 5.2 ohms. R is equal to 5.2 ohms. So in this case, the total power dissipated in all the three resistors is given, that is 10 watts. That is equal to V square, applied voltage square, divided by R equivalent resistance of all the three resistors. So equivalent resistance is R plus parallel equivalent of 12 and 8. Parallel equivalent of 12 and 8 is 4.8. So 4.8 plus R is the total resistance of the circuit. So V square divided by 10 square divided by R plus 4.8 is 10 watts, from which we can find out the value of R, which is 5.2. So that's all for today. Thank you very much for attending this session. If you like the video, please share it among your friends, and also subscribe for the channels, and press the bell icon for notifications. Thank you very much.